I'm hoping I typed everything correctly. Is it BUN or BURN? Okay, I have it correct. There we go. Okay, you are now live on screen. So, everyone, I would like to introduce my fellow Planetary Science Institute colleague, at Loki Volcano on Twitter, one of my favorite volcanologists. That's the word. Welcome. How are you doing this Saturday?
Oh, good. Thanks for having me. Doing pretty well. It's getting busy getting up to the holidays, but
It's true. Now, as many members of our community know, I quietly and sometimes loudly stalk volcanoes on Twitter, waiting for the next great eruption with a webcam nearby. And you use cameras way better than webcams for a lot of the things. Okay, I'm screen.
His name is truncated.
What did I do?
On her name on her screen.
Is there
It's truncated.
is there a missing space?
It's RATHBU, comma.
Oh, I left the N off your name entirely. Sorry, I'm getting corrections from the audience. I literally can't see the screen that I'm typing on from where I'm sitting, so there's a certain amount of prayer involved.
no problem. That happens a lot when using cameras to look at other planets too.
Yes. So can you explain a little bit about what all it is you do? And I'm going to duck sideways to fix your name.
Okay, no problem. Yeah, so I like studying moons in the solar system. I think Jupiter's moons are some of the most interesting places that we have in the solar system. My favorite moon is Io. I like to say I'm part of Team Io. It is the most volcanic place that we know about anywhere in the universe. And it is just fascinating to me that you can take an object the size of our moon and have hundreds of active volcanoes at any time on it. And so I'm trying really hard to understand it. Yay! Io ornaments. Oh, I love it.
Yes.
Oh, the other side had Loki. Loki's sort of the horseshoe shaped one. I don't see it there. I saw it a second ago, I thought. There it is. It's upside down.
There.
Yeah, that one's Loki up there with the horseshoe shaped near the top.
There's better pictures online, people. Oh, now I can see it easily. Okay.
Yeah.
There. Okay.
It's a great volcano.
Okay. So how I did not know that I don't know how I didn't know. I didn't somehow know that interplanetary volcanologist was a career. How did you discover this?
Oh boy. I kind of fell into it. Knew I wanted to study planets, went to graduate school, started studying planets, and discovered these moons that were just, I thought, so much more interesting than the planets themselves. Io is just so active. I didn't realize there was any place. When you think about astronomy, people look and they want to look at things in the universe. And usually you look once and you're like, okay, I saw it. That's cool.
Yeah.
I'd like to see something similar. Or I'd like to see, it in better detail. But when I discovered, I mean, it's not like I discovered Io. When Io came into my life, it was like, wow, here's a place you could look at it once a week and it looks different. That's pretty cool.
And one of the things about your research that I particularly love, because as a variable star person, the first research paper I ever worked on, I was using 100 years of data that was collected by generations of astronomers. Now, we don't have generations of data for the moons of Jupiter in any resolution. And this is actually, I need to point out, every item on the tree behind me is a moon of Jupiter. So I have a planet, I have a tree of Galilean moons, and a few extra moons. Um, so you started studying Io as a graduate student, and you made a key discovery with your research team about, well, it turns out some worlds have a periodicity to them as well.
Yeah, they've been looking at Io. I mean, it is pretty cool that the volcanoes in Io we've known about for about 45 years, and that's all, which is kind of amazing because that's about my lifetime. And we really didn't know that Io or other Galilean satellites were active before that. So I got involved about 20 years ago, and they're already had about a decade of data. The group I joined had about a decade, and they had ground-based data because at that time we'd had the Voyager spacecraft, Galileo spacecraft was in orbit, but of course spacecraft can't really live a long time. It's hard to get a lot of data over a long period of time. So there were these ground-based observations, about a decade of them. And I joined the team and continued those observations, and the brightest volcano you can see from a ground-based telescope on Io is Loki.
Yes.
Every time we look, every time we aim our telescope at Io, we see Loki. It is always active at some level. It's always measurable. And we thought, well, this is interesting. We have 10 years of data. What if we, look to see what it's doing? Is there a pattern there? And I happen to work across the hall from some comet scientists who they study, periodicity in comets, and gave me some mathematical tools, or showed me some mathematical tools, and we used those and found out at that time that Loki had erupted about 6 times on a pretty regular schedule, 540 days. With and you're using these statistical techniques, and they said this is a very high probability that this is, a real pattern in there. This isn't just some artifact of the data. And we said, wow, that's really interesting. This thing is,
and this isn't like when we talk about Katla goes off every 300 years, or the Cascadia fault line goes off every 300 years. This is more precise than that.
It's 540 plus or minus 10 or 20 days.
Yes.
So it's pretty good. Unfortunately, it's a volcano named Loki, which I did not name. And the minute I published a paper that said Loki erupts every 540 days on a regular schedule, it stopped doing it. And so we had observations. We had about 5 years of observation, maybe a few more, where we had no idea what Loki was doing. We're just like, okay,
no.
Nothing's happening. Then it started being periodic again around early 2010s. And this time the periodicity seemed a little shorter. I think I was looking at 450 days. And we had 5 eruptions with that schedule.
Uh-huh.
And then I opened my big mouth again last September at a conference and announced very loudly, Loki's periodic again. It will erupt in October. And it didn't.
Oh, God.
Has
it gone off yet?
We don't know. This is the tricky part, because Jupiter is so close to the sun right now that our observing hiatus. We won't be able to observe again until February.
Will you have any way of knowing if it went off during the hiatus?
If it's active in February when we look at it, we'll be like, okay, it started during the hiatus. We don't know exactly when. There's a chance. There is a group that's been using the Keck telescope and Gemini to get observations. I don't know if they're getting observing time right now. I haven't spoken to them in a few months, So it's possible she's filling in the gaps,
Oh,
but I
geez.
don't know.
Now,
So yeah, my main take home message is don't name features after trickster gods. It's
no,
good enough for you.
no, that seems like a good idea. Now, you have this gets periodic, goes to chaos, gets periodic, goes to chaos. Is there at least a periodicity to that you can tell, or is there not enough data?
There's not enough data, unfortunately.
That is sad.
Part of the problem was ground-based observing time is difficult to get. You have to submit an application to get the time.
Right.
The observing for this is also tricky. A lot of telescopes have moved to Q observing, where you don't have to do anything and you can actually sleep when your body wants you to. This observing is trickier because you're watching. In order to see Loki, it's actually kind of an interesting technique that was developed. Io is so small, so far away. It's really hard to see from an Earth-based telescope.
Right.
So what we do is we wait for Io to disappear behind Jupiter's limb. And we look at the total brightness of Io as it disappears behind Jupiter. And we look as that brightness jumps down. We're like, oh, a volcano just went behind Jupiter. There's a volcano somewhere, along that line of Io across Jupiter.
That's so hard.
Yeah, it's a tough observation to do, and so you have to have a human being doing the observations, and so you have to be up in the middle of the night. And there were periods of time where no one was looking, either because we couldn't get telescope time or didn't apply for telescope time. Yeah, so it's a tricky observation, and we're hoping to get more data. As I said, in February.
How big a telescope do you require?
We're using a 3-meter telescope. We might be able to get away with a slightly smaller one, but the specific telescope we use, the Infrared Telescope Facility, IRTF on Mauna Kea, has dedicated time for planetary work, which helps us to get some time. And that's where we've been doing the observations since the mid-90s.
So, wow. That's a challenge. Now, before going into how infrared is the way to go for things like this, I want to take a moment to thank some people. We had a donation come in from Open Cage. Thank you so much for the donation. We had a sub come in from Crunchy. Thank you, Crunchy. We also had a sub come in from Mythtown. For those of you joining in and not sure quite what you have stumbled into, my name is Dr. Pamela Gay, and I am one of your hosts for a 40-hour-long hangout-a-thon, our modern-day equivalent of the old-school telethon, where we are going to entertain you as best we can for 40 hours while we work to raise money to keep all of our programs going through 2020. We are working to raise funds to cover the costs of our podcasts, our streaming services, and to just keep bringing you opportunities to do science. Our goal is to be able to pay our staff an equitable wage and stop asking them to sometimes do things for free. We don't actually ask them to do that. I just keep discovering they did it because they're good humans. Please help me pay my good humans and give. If you've ever said, why doesn't science get more money? This is your chance to get science more money. And one of the people I'm lucky enough to get to work with is our guest this hour, Julie Rathbun. And she is comparative volcanologist the correct term, or planetary scientist?
Oh, I make up a new term every week, depending. I mean, that's the nice thing about planetary science. It's such a young field. We can kind of make up new jobs for ourselves.
Whatever you call yourself, you get to study world-spitting stuff out. I love volcanoes. I love volcanoes so much. I am horribly allergic to volcanoes. If you're allergic to sulfa drugs, you may have problems dealing with volcanic fog. Dear audience, now you know. You can learn from me. But here on Earth, we have all these different volcanoes all over the planet. Sometimes we can predict one is going to go off. Sometimes horrible accidents happen, as it happened in New Zealand a couple of weeks ago. On Io, the volcanoes are driven by completely different processes, and this leads to different behaviors. Can you describe the kinds of different things that lead to volcanoes coming into existence?
So there's several things that make the volcanoes on Io a little different than the volcanoes on Earth. And first of all, how they're similar. The rocks on Io are very similar to the rocks on Earth, I mean, in general. The biggest difference really is that the lava on Io is very thin. It's got a very low viscosity. It's very runny. So volcanoes on Earth have different categories. Volcanoes on Io would be most similar to volcanoes in Hawaii. And they've got very runny lava. In that sense, if you were living on Io, they're a little safer. They're not explosive style volcanism that runs over. I mean, if you've ever seen a Pahoehoe lava flow in Hawaii, for example, they're very dangerous to property, but they're not usually dangerous to people because they move pretty slowly, and you can just
you see people feeding things into them occasionally.
Yes, quite often. So it's a very runny lava. So I'm not usually talking about. I think when most people think of volcanoes, I found this through talking about Io for many years, they think Mount Fuji.
Yes.
Something very big, stuff coming off the top, blowing its head. Loki in particular is a lava lake. So it's more similar to lava lakes in Hawaii. My background's physics, so I tend to simplify everything. So I think of Loki as a giant bowl of liquid rock.
Cool. I approve.
A giant bowl of magma, and it's fun to say magma. So it's a thinner lava. So that's one difference between Ionian volcanoes and terrestrial volcanoes. The other difference is the ultimate heat source.
Yeah.
On Earth, the heat source is for the most part leftover heat from when the planet formed. Mm-hmm. When we went to Io, we knew of a few heat sources that are predominant in the other solar system, and we discovered a new one that nobody knew about. And it's called tidal heating. And basically, because Io is so small, it's orbit around something so big, and it is being pulled on by other moons, the thing is just getting squeezed. Gravity is squeezing the heck out of it. And when you squeeze something, it tends to heat up. It's frictional heating. The common example is a paperclip, bend it back and forth, it'll warm up. And since Jupiter's and these other moons are just yanking on Io all the time, that creates all the heat. And if it were for tidal heating, I mean, we expected when we sent the Voyager space probe, people expected Io to look like the Earth's moon. That was the expectation. Yeah. And this is part of the Io story I just love, is that there was an engineer at JPL, Linda Mirabito, who was looking at the engineering images coming down from Voyager as Voyager was getting close to Jupiter, just making sure that its trajectory was correct. She wasn't actually intending to do science while she was doing that. She just wanted to make sure the spacecraft was safe and doing what it was doing. And there's this
accidental science.
Which, let's face it, a lot of it is.
Yes, it's true. It's true.
Accidental science, but you had to be purposely sending, a multi-million-dollar spacecraft there to do it. And she saw this image of Io, and there were two things that were weird about it. One of them was there looked like there was I guess the most obvious thing was that there was looked like there was a moon behind it. There was something coming out of it. And so some of these Ionian volcanoes, it's not really explosive volcanism that goes up. It's there's no real atmosphere in Io. So when the volcanoes erupt, they interact with whatever ice is on the surface and cause that ice to immediately go to vapor. And that vapor just goes whoop, And you
Oh,
get these
geez.
vapor plumes that are huge. They're hundreds and hundreds of miles wide and tall. And she saw one of these in her images and is like, what the heck am I looking at? Because we expected this world to be dead, to not have any activity. And so a giant vapor plume was very surprising.
Yes. That, yeah. I like when you first see that, you don't necessarily know how long did it take them to figure out what the heck they were looking at?
It was a little before my time, so I'm not, I don't have firsthand experience with the
Okay,
story.
I don't know what the
Yeah.
stories are that get told and retold over the years.
Oh, that's true. That's interesting. So I find the most interesting things about it is that there were a group of theorists who were calculating how much heat the Earth produced in our moon due to tides. They said if the moon could raise tides on the Earth and the water could move, then could the Earth raise tides on the moon? And they did all this physics and all this math, and they came up with, oh, it's not very much. But they looked at the formulas and realized, and this is one of the things as a physicist I love about formulas, you look at the formulas and go, wait a second. This depends on how big the planet is you're orbiting, and it depends on the eccentricity of the orbit, how non-circular it is, how old it is. And wait a second, there are other moons in the solar system where these terms would be huge. So they plugged in the terms for Io and went, oh, wow. That is a lot. And they published a paper that said, we predict there to be some kind of geologic activity on Io. Oh, and wow. It got published. And my understanding, the stories that get told, my understanding is that no one on the team, the Voyager spacecraft team, had time to be reading the literature.
I totally believe that. With Osiris-Rex, this summer, I felt like it was this constant battle of us versus the rocks, and the rocks were definitely winning. So this was predicted. It was then seen, and then someone had to get these two groups of humans together.
Yeah.
Oh, geez.
And I'm not sure how that happened exactly, who finally went, I saw this paper, or I heard about this paper, or maybe somebody was at a conference and saw something, but, or maybe there was a photograph that got released and one of the theorists called up the scientist. I'm not really sure how it happened, but I love that story of discovery, that somebody predicted it and then it was discovered independently within, a month is pretty amazing.
That is amazing. And I also want to say it's amazing that Zenoswa, I don't know how to say your name. Zeno, we're going to go with Zeno SW. Thank you so much for your $20 donation. Thank you so much. You make the science continue to flow. We must let the science flow. But volcanoes are science. Why did I not know this in high school? So many things I did not know were career options in high school. Now, people use the phrase cryovolcano and volcano and don't often explain what are the similarities and differences between these things, and then there's geysers. In this continuum of stuff getting spit out of the surface of worlds, can you help us make sense of geyser versus cryovolcano versus magma volcano versus whatever it is that's on Ceres that's sending salt up?
I'll see what I can do.
Okay.
One of the things I'll just sort of back up on, maybe an interesting side story, because it's kind of related to your previous guest. Studying geology of other planets is tricky because you're mostly looking at images.
Yes.
And then you're sort of comparing things to the Earth. So you're looking at shapes and textures and lines. I discovered similarities when I started working with an abstract artist who we got talking. I was like, holy crap, the words you use are exactly the same things we use as photogeologists when all we have are images. And it is really fascinating. That's how we sort of guess what we're looking at. We're like,
right.
Impact craters are completely round. Volcanoes are usually blobs. They're somehow blobby things. Rivers are squiggly lines. And any kind of tectonic mountain building feature is a straight line. And that's the simplification, but that's like the very introductory level of planetary geology, photogeology, looking at images. And so all of these comparisons are based on rock. They're based on what we look at on Earth, and then, the Earth's moon, Mars, things we looked at first. But then you get the outer solar system, and with the exception of Io, all the other moons are ice. They're all ice worlds. And so you start looking at these worlds made of ice, and you're trying to interpret what the heck you're looking at. And most of your vocabulary is rock-based. So you see something blobby and you want to say, I think that's a volcano. And then you're like, well, is there such a thing as an ice volcano?
Right.
I don't know. And then you start creating new words like cryovolcanism, which is supposed to mean ice volcano. I don't know why we didn't just say ice volcano. Nobody asked me.
Cryo sounds more sciencey.
Yeah, it was somebody trying to sound, great science. But yeah, you see these features on these ice worlds, and you're like, okay, this looks like some kind of flow feature.
Right.
Well, what's a flow feature on Earth? It's probably a volcano.
Right.
And so we'll call this cryovolcano. So I have done a little bit of work studying Io's neighbor, Europa, which I'm sure is on the tree behind you, but it's not nearly as cool looking as Io.
No, it's really not. There it is. I used it as the moon earlier today. So you can, it also took a dent. So this is Io. You can just make out its cracks. You probably can't actually. But
yeah, Europa basically looks like a giant ball of string.
Yeah. It is Europa, I promise you. Thank you. Thank you so much, Ryan Vade, for $20. Ryan was a programmer with us while he was a student, and it's his WordPress plugins that make a lot of the random stuff around here involving Twitch and Discord actually happen. So thank you and my dog is moving the camera again. This is what my dog does every few hours. He moves the camera. Okay, you now get to see the brick wall. It's a nice brick wall. So, thank you, Ryan. Why do I have a dog growling? I think there's another human. Aha, there's another human. Sorry, I got distracted by the former student of code we still use in the chat.
That's really cool.
And then my dog started growling because we now have an R-instro back in the studio and a dog that dislikes men at my feet. So, you were talking about ice and cryo and how cryo is a fancier, sciencey word than ice volcano, and you did not name it. So help us understand what is driving these cryovolcanoes and how folks came to understand lumpy thing on ice world also counts.
To be honest, I think we're still in the process of that. We actually had a big meeting about a year ago on cryovolcanism in the solar system, where there were a few people there who actually didn't believe it was a thing. And a few people there who believe it is a thing, but we've never actually seen real proof of that thing. And so there's a lot of debate about what are we really seeing. On Europa, we have, you said, lots of cracks, so lots of tectonic features. We know that. There's some places where there are mounds, very small mounds, that look like something's pushing up underneath the surface because you can still see the cracks going across it. We have something called chaos regions, where it looks like the ice has broken up into rafts, and those rafts have sort of moved around on top of the ice. And so there's some, so what causes the chaos regions? And there's a lot of debate about where those come from. We know they're young. we know that it's some geologic process that is very different than what happens on Earth.
Young areas cause chaos? That sounds rather human of them.
Yes, that does.
Sorry.
That's okay.
So, and then we also have weird things like Saturn's moon Enceladus that has these tiger stripes. And did you see the recent paper? I think it was in Nature, on how one crack probably led to all four cracks and no more cracks.
Oh, I haven't seen, I've been meaning to read that one, actually. I heard somebody was telling me about that, and I'm like, I need to read that one, and I haven't actually gotten my hands on it yet.
So the core idea basically was, it was a random throw of the dice on whether or not the thinner region in the northern or southern pole would be the first to give. It turned out the northern pole initially cracked open, and where it cracked, a geyser, or a whole string geyser, erupted out because there was so much pressure on the inside. It was that pressure on the inside that cracked the surface, just like an orange that has too much juice or a tomato with too much juice will end up cracking the skin. And once this crack came up, the material flying up would then fall down rotation. So it would go up, the world would rotate, it would come down, and it would always come down the same distance because gravity is consistent. And the combination of snow piling up on the surface and continued excess of pressure on the interior led to a new weak place that ended up cracking open. Rinse and repeat this for all three of the additional cracks that ended up opening at intervals. And it eventually reached essentially an equilibrium point where those four places are all able to keep puncturing each other open, so that it's like a wound that isn't allowed to heal. But these four are just enough to relieve the internal pressure to prevent additional cracks from being able to open.
Oh, that's really interesting. I really have to get my hands on that paper now.
It's one of those delightfully straightforward results where you read it and you're like, someone spent years figuring this out, and now it's going to become a homework assignment.
Yeah. Yeah, it's like, this makes sense now.
Yeah. Why didn't we think of this earlier? It's awesome.
Yeah. And I mean, and Enceladus is another bizarre place where they weren't expecting much from it when we sent the spacecraft out there. We had a few images from Voyager, which showed that the surface was smoother than we expected.
Yes.
When you expect a dead world, you expect all those impact craters, and there weren't a lot of impact craters, or at least not as in certain terrains, certain places. And when the Cassini spacecraft got there, it actually took quite a while for the scientists on the Cassini spacecraft mission to believe their data, that there were, because, what is the old Carl Sagan phrase? Extraordinary claims take extraordinary evidence. I think that's a Carl Sagan quote.
Yes, it is.
And nobody really wanted to say there's giant plumes on here until they were absolutely certain that they weren't an artifact of the camera system with, internal light reflecting around or something like that. And it took, and this is why we have to send multiple instruments and not just a camera. It took agreement from multiple instruments. The camera seeing the geysers themselves, a thermal camera, infrared, one of my favorite techniques, seeing heat on the surface. And I believe, I'm trying to remember if it was magnetometer data or if it was like a mass spectrometer flying through that. Actually, it was some kind of what they call an in situ instrument, which is not my specialty. Right. And they also saw something, and it took like 3 or 4 instruments seeing things before they went, well, all right. The best explanation for this is a plume. Of course, it's interesting now that we're talking about plumes on Europa with much less evidence than it took to discover plumes on Enceladus, because it's not as extraordinary anymore for it to be a different moon, to see them in the second place. But those are definitely,
again, multiple instruments.
Yes.
And
although the thermal data, I actually just had a paper come out where we looked at thermal data
Uh-huh.
For Europa, there is absolutely no thermal data that suggests there are hot spots on Europa. Now,
Oh dear.
granted, the data is of a low quality,
Right.
but we've mapped about, I want to say 20 to 50% of the surface at various. It's not really resolutions when you're talking about thermal. It's various sensitivities.
Yeah.
But if there was something over that 50% of the surface that was as warm as liquid water, we would have seen it.
And what you're starting to get at is I distracted myself because volcanoes about half an hour ago away from infrared light. And infrared light, for those of you who don't know, it was actually discovered by accident by William Herschel. He had light from a telescope going through a prism, creating a rainbow on the floor. He had a thermometer. I don't remember why. He put the thermometer beside the red part of the rainbow and saw the temperature go up and realized he had detected something that he couldn't see with his eyes. There was clearly something there that didn't exist in the rest of the shadow. So redder than red, infrared, was discovered by accident by William Herschel. And the longer wavelengths of red are starting to behave more like radio signals. Now, with radio, when you're tuning your dial, what you're trying to do is find some place that has enough intensity to trigger the antenna to go, yes, I see a signal. Our eyeballs work kind of similar, and our detectors work kind of similar, where they're looking to see how many photon counts. It's a count of individual particles. So the triggering is slightly different. And so you don't count photons the same way in infrared as we do in optical, and heck, gamma ray astronomers name their photons sometimes. Can you help our audience understand this unusual color of light a little bit better?
Oh, I mean, my favorite tool, and I love this because having a physics background, so many physics tools are things that tend to be masculine coded in our society. So I love the fact that the tool I'm about to mention is more feminine coded. I've seen this a lot on Food Network. Some people cooking. There's an infrared gun you can buy from cooking stores that you aim at your pan, and it tells you if your pan is hot enough to cook with. It is really useful for like cast iron, because you can't really tell how hot the cast iron is.
Right.
And I love to cook. And so I have one of these guns my husband got me many years ago as a gift. I took it out to Yellowstone National Park several years ago on a vacation there, and it works like my spacecraft instruments. You have to be within a certain distance.
Right.
And the hotter it is, the further away you can be. So that's very similar to our spacecraft data. The cooler it is, the closer you have to get. And you could stand near these hot springs that they have in Yellowstone, or the bubbles or the geysers, and aim this thing, and you can tell the temperature of the water or the steam or the rock or whatever it is you're aiming it at. And it's exactly the same as the data I'm taking. We actually did an event. This was over a decade ago. We did an event somewhere in Southern California for folks from PSI who were donating, and it was at somebody's house who had a pool. And it was summer, and it was really fun because you could take this infrared detector and aim it at the ground that was in direct sunlight, the ground that was in the shade, the pool, and you could measure all the surface temperatures of all these things.
Okay, you definitely need to bring this to the next PSI retreat. Oh my goodness, I need to get one of these. I have a turtle, and I'm always curious just how warm his basking spot is, and I clearly need to get one of these suckers. Now, there's lots of reasons to look at things in infrared. Snake's vision is sensitive to the shortest wavelengths of infrared, allowing them to find warm mouths against cold leaves at night. Now, clearly you're not looking for warm mice against cold leaves, and you actually use infrared for an entirely different reason. Can you explain why infrared is so useful?
So there's a couple of reasons. I mean, an IO, you're literally measuring the hot stuff. It's something
Yeah.
that's warm, and you can measure the temperature of the hot surface. If you're not measuring, so anything that's active, and it's the same thing with Enceladus with the tiger stripes.
Mm-hmm.
Anything that's geologically active, there's stuff moving around, and just like with the tidal heating, there's some friction at the very least, and it's going to warm things up. So if something is currently active, it's going to be warmer than something that's not active. I don't think that's too surprising. So that's one thing that we use it for. Another thing we tend to use it for is we look at how surfaces respond to day-night temperature changes. And I lived in Southern California for many years, and you could talk about going out to the beach and how the sand heat up really fast and it got really hot in the middle of the day, but then at night it cooled off very fast. Whereas something bulky like a rock, or I was fortunate enough to have a convertible when I lived down there, and at night you would drive under underpasses.
Yes.
And you feel the underpasses radiating back at you, and it's all the heat during the day. So by looking at temperatures during the day and at night, you get some idea of the physical properties of the environment you're looking at, whether it's sandy, whether it's rocky. And they've used this technique on Mars to figure out how rocky landing sites are, so that they can figure out if they're safe to land or not. So if you don't have high resolution imagery, you could look at these day-night temperature swings. The measurement's called thermal inertia.
I didn't know you could use that for texture.
Yeah, so you can use it to know. So on Mars, you basically assume every surface is a mixture of rocks and everything else is sand.
Right.
And if you want to know what percentage is rocks, if you know the thermal inertia, you now know what percentage is rocks. And if there's very low percentage of rocks, it is very safe to land.
That cool.
And we're planning on using the same technique at Europa, and hope that it works for ice.
So I'm moving a bit. Pardon. My dog keeps moving the camera, and he moved it in such a way that I can now get closer to my space heater. So I'm actually kind of okay with my dog.
That is helpful.
It's a cold day here in Southern Illinois, and I live in a really old farmhouse. Now, with Europa, we have the Dragonfly mission that will be going there in 2033, I believe, is the
That's Titan.
That's Titan.
Titan is Dragonfly. Yes.
Okay, Titan is Dragonfly. You're right. Yes. And what year is Europa Clipper planned for?
It's still not set. They're looking 2023, 2025, that sort of time frame.
Okay. Slowly. Now tell us what you know about this planned mission.
So Europa Clipper is, I think, a really cool mission. Basically, Europa, the tough thing about Europa and Io is that they're hard to get to. Jupiter has a huge magnetic field. It's a huge magnetic mess near Jupiter. Since Io and Europa are relatively close to Jupiter, if you want to go to Io or Europa, you got to deal with this high radiation environment. High radiation, electronics on spacecraft do not like that high radiation environment, and it's bad. So, what we'd really like for Europa is to have an orbiter. We'd love to have a spacecraft orbit Europa, but you don't last long when you're orbiting Europa. So what Clipper's going to do is clip by Europa. It's going to orbit Jupiter. And on every orbit around Jupiter, it's going to fly by Europa, get very close to Europa.
So there's a resonance orbit.
Yeah. So approximately every 2 weeks, it's going to fly by Europa. Hopefully looking at a different part of the surface, at least slightly different part every time we go by. And the engineers at JPL are doing a fabulous job coming up with trajectories for us to look at and what parts of the surface we might get to see. And by doing that, it's in the radiation field for a very short period of time, just a couple of days, and then spends the rest of the 2 weeks sort of in the safe zone. and gives us 2 weeks to analyze our data. And then it goes back down, collects more data, and gives us another 2 weeks.
That's a nice. So one of the big frustrations with New Horizons is it got all of this amazing data, and then we waited.
Oh, yeah.
And if you were actually orbiting Europa, your data acquisition rate would exceed your data return rate. So you'd have to like throw out data, which like none of us want to ever do.
Yeah.
And so this particular orbit means you don't have to throw out anything.
Yeah.
You can focus all of your energies when you're at Europa and just get the data, get all the data. That I didn't know about the orbital planets. I didn't understand where Clipper was coming from as a name, and that is super clever.
Yeah. Yeah, it was really, there was a lot of people who just sort of, including myself, who thought, we've done the flybys of Europa. We had the Galileo mission. The next logical step is an orbiter. So clearly we just need to figure that out and we need to do it. And it was very difficult and very expensive. And somebody said, well, why not just do it this way? And that's genius.
Yeah.
Because you're right. It gives you the right amount of data. It gives you the right amount of radiation, the least amount of radiation you can get. It's just a great idea. Similarly, I've heard a similar idea for studying Io, which I thought was genius. And I have to give credit for this idea. Zibby Turtle, who is the lead scientist on the Dragonfly mission to Titan, a lot of her research has been studying Io. She's part of Team Io, even though she also loves Titan. And we had a conversation about what's the best way to study Io. And I thought she had this brilliant idea where now that we're building very small spacecraft, NASA's trying to get, what are we calling those? CubeSats.
Right.
NASA likes that term. Send a giant spacecraft with a bunch of CubeSats and have it in Jupiter orbit parked outside. And then just every once in a while,
eject
send
a sacrificial.
And it can orbit Io or can fly by Io and collect data for a little while. And if it dies, of course it's going to die. The radiation is going to kill it. But then you got more.
This takes what they did with Hayabusa 2 to a whole new level. One of the things I loved about Hayabusa 2 is it just kept throwing stuff down at Ryugu. And it was someone in one of our live streams who made a quote along the lines of, basically the Japanese took every robot they could think of and threw it at Ryugu. And I'm sure they could have thought of many more robots. But
Japan is very good at thinking up robots.
Yes. But this whole idea of we're not going to just lower our spacecraft and grab a sample. They did that, but they also like throw this, throw that. Sure, if something doesn't work, you'll lose that few tens of thousands of dollar thing. And yes, a few tens of thousands of dollars is what we're currently trying to raise. That is a not so subtle reminder, people. Please share the word. Anyone you know on Facebook who has ever said, we need more money for science, we need better science education, go tell those people. Donate here, please, please. Holiday science. But with this notion of these small tens of thousands of dollar satellites, this starts to become the kind of thing that's the same price that you might spend on all of the research hours for a graduate student at telescopes. So now what is a graduate student's worth of equipment is a satellite you fling at a moon of Jupiter. And this opens up science possibilities for so many people.
Yeah, it is tough. And that's actually an interesting point because a lot of the research I do, I use spacecraft data. Mm-hmm. I've used data from the Voyager mission, from the Galileo mission. I use New Horizons data because New Horizons, people forget, it flew by the Jupiter system on its way to Pluto.
2005?
7. It launched in 5. It flew by Jupiter in 7. And it took some fabulous images of Io's volcanoes. I mean, absolutely spectacular images of Io's volcanoes. And we learned a lot from that mission. But you can't rely on just spacecraft data because it's few, there'll be large gaps. So that's why we're using the ground-based data to fill in those gaps. We're trying to use the IRTF data and the Keck data and the Gemini data to try to fill in those gaps.
I need to share what Bill Nash just put in the chat with you because I'm trying not to die laughing.
So I just saw that.
So Bill typed, aliens are going to show up and the message will be, please stop throwing things at us. Only because it's unethical to throw graduate students at moons for science. It's true. It's true. So, and Paranor says he sees Angry Hamster. Yes, Angry Hamster is sitting just off camera. He will now sit on camera.
You might want to go get thrown at a moon at some point. Maybe one of the ornaments or...
It's true. I love the fact that he's just like angrily peering over. Yes. Okay. So we are running down this hour. I clearly could talk volcanoes for hours, days, months. If you
ridiculous.
ever really have any citizen science, I kind of like volcanoes. Would love to work with you. Not gonna lie. I will be overly enthusiastic for you anytime you wish. One
thing I will tell people to look out for, somebody asked if this was a while ago, somebody asked if any spacecraft were currently looking at Io's volcanoes. Mm-hmm. The Juno spacecraft was in no way designed to look at Io. No, it was designed to look at Jupiter's atmosphere. It was only supposed to look at Jupiter's atmosphere. But it actually has amazing images of Io's volcanoes. It's an instrument called GEROM. It's out of a group in Italy built this camera. It's an infrared camera, and they put out a couple press releases. All the data is available. So there've been a few citizen scientists putting together some images I've seen on Twitter. It's amazing. You can see which volcanoes are active, and you can see, just this globe with dozens of hot spots on it. I'm something else.
That is all awesome. And thank you, Broken Symmetry, for all of the bits. The doggos are asleep, but let me see. Malachi is not about to get on camera, but I will give him a treat. Here, Malachi. So are there any parting words that you would like to leave our audience with? Anything you think everyone absolutely needs to know?
For a while, I've been trying to convince people that planets are overrated.
Yes.
I'm a planetary scientist. I love the solar system, but it hurts me to my core that we focus so much of the solar system just on planets.
We need to rebrand.
Yes.
I personally make an effort to say worlds instead of planets. World scientist sounds more like political science. That's a little bit scary. Yeah. But we need people. Some of you out there know how to name things better than science. We should not be allowed to name things. This is how you get dark matter.
Extraterrestrial geologist. Can I just be an extraterrestrial geologist?
Yes.
That sounds kind of cool.
From henceforth, it shall be extraterrestrial science.
It seems to make sense. That's what we're doing.
I like it. I like it.
Anyway, that's a parting thought.
That is an excellent parting thought. So I'm going to switch views and say goodbye for now, but not forever. I hope we can have you back and not be fundraising. And I definitely look forward to seeing you. And I'm so glad that we work together at the Planetary Science Institute.
I am so glad you've joined us at PSI. Bye. Thank you for having me.
Bye-bye. So our next segment is going to be with George Kramer. It's going to be hosted by Susie. I will be setting that up for you in just a moment. For those of you who aren't subscribers, I'm about to torture you with an ad, and I apologize. While Susie is hosting, we're going to do a little bit of tech around here. But before we switch over to her, we will be restarting the stream. So here's what is about to happen. I'm going to run a 1-minute ad, which subscribers won't be forced to see. I'm so sorry, all the rest of you. This just helps. It helps. We do what we can. If we hit 40,000, I won't run ads again. Money. I'm sorry. We are going to, after that occurs, restart the stream. So it will go dark for a moment, come back up. This is to make it easier to archive the content we're creating. And then Susie is going to be hosting a discussion of the moon and awesome sauce with George Kramer. So I'm going to click go on the ad, if I can find the correct mouse. Thank you, Bill Nash. There are subs flying in all directions. Thank you so much. So a lot fewer of you are now seeing that ad. So while Susie is hosting, we'll work on cleaning things up around here, syncing up the bits to the goal that you see beside us, syncing up the subs. It is like a grant that everyone gets to put time into. It is perfect. Thank you. So in 10 more seconds, I'm going to restart the stream real fast. You hopefully won't notice much of a discontinuation, and there should be no craziness. On the other side of the restart, I'm going to set up the screen for Susie and George, who has the best ever room she is streaming from. You have all seen this on the weekly Space Hangout. Okay, so we are done with the ad. I'm now going to restart the stream.